Hello friends, let us continue our discussion on understanding the creep behavior of a material as a whole. So, we defined the creep as the time dependent behavior of a material to an imposed mechanical condition. So, this imposed mechanical condition is a constant stress, and this time dependent behavior becomes prominent at high temperature or the temperature more than the ambient temperature. So the other factor that remains constant is the temperature. Now, since we are nearing the module that talks about the creep of the material, we are considering the creep behavior as a whole. In the early lectures, if you could recollect, we sectioned the creep behavior into different stages, and this sectioning was largely based on the creep rate or the strain rate exhibited by the material during that particular duration of time. So, if you consider a crystalline material with a definite, or you impose a definite stress and temperature, the characteristic creep curve or a representative creep curve would look something like this. So, this we have seen many times in this lecture series, and now what we have is we have a section wherein you have the combination of instantaneous creep and the transient creep, a steady state creep, and the ultimately you have your tertiary creep or the accelerating creep. Now, from the beginning, or when you wanted to express or have an expression for this overall creep behavior, so we saw this was initially proposed by Andrade in the year 1910 to 1914, and his expressions were largely empirical or phenomenological, meaning he observed several crystalline material at a given temperature under a constant loading condition. He gathered all those data and he tried to fit the curve that he arrived by experimenting on different material, and while he wanted to fit the curves, he ignored a particular stage of this creep curve. So the stage that he ignored was the tertiary stage. So this tertiary stage or the accelerating stage, which ultimately leads to the failure of the material, was largely ignored from the beginning by Andrade. Like from the year 1910 to 1914, when people wanted to understand the creep behavior, or when they wanted to quantify the creep behavior, they largely ignored the tertiary creep, and this had there was a reasonable consideration which allowed for the overlooking of this particular tertiary stage. So one of the reasons was people, when they wanted, or when you understand or study the creep behavior of a material at high temperature, you are orienting your test procedure, or you are orienting your investigation for a particular application. So this whole creep behavior or the creep study is directed towards a high temperature applications particularly, and that is the reason why we are considering this particular behavior of the material in the context of high temperature materials. So whenever we are studying the creep behavior of a material, it is directed towards a particular application, and when we talk about an application, we are largely interested in two aspects of a material when it is used in the application. So one is the life of the material, the other is the behavior of the material. So whenever we want to discuss the role of a material in an application, particularly an high temperature application, we focus on two different things. One is the life of the material and the other is the behavior of the material. So behavior is rather a generic term. When you want to have a technical term to replace this behavior, it would be strain or the deformation of the material. Strain or deformation of the material. So we are interested in these two aspects of the material when it is used in a particular application. Now, when we talk about the life of a material at high temperature, we saw earlier, or as we discussed earlier, the life of a material in a particular application, it largely comprises of the steady state condition here. So this is just a schematic curve, and even here you could see the curve, it largely comprises of the steady state region here, and in the similar way, when you have a material that is being used in an application, the life of the material or the substantial part of it, the material spends in the steady state condition. And that is the reason why when we talk about a given mechanism, a given creep mechanism for the consideration of a definite stress and temperature, the expressions that we get for a definite creep mechanism is dependent on, or it is expressed as the creep rate at steady state condition. So when you focus on the life of a material, then you are largely considering the steady state behavior or steady state creep behavior of the material. And in the previous lecture or the one before that, when we considered the transient creep of a material, we saw when we focus on the behavior of a material or the deformation exhibited by a material in an application, then we began by considering, or we consider the strain of the material. So the strain exhibited by the material during the creep testing. So we have two aspects that we need to consider when we want to use a material for an application. One is the life, and other is the deformation that the material exhibits during that application. And that deformation in the creep behavior, it is largely rendered by the transient, the combination of transient creep and the instantaneous creep. So the combination of the transient and instantaneous creep, which we refer to as the stage 1 of the creep, it largely contributes to the strain we observe in a material during the creep testing. In the similar manner, the life of the material as a whole is largely dictated by the duration the material spends in the steady state condition. Now, when we talk about these two aspects, when we consider these two aspects in an application, after the steady state condition, when the material begins to deform excessively at a higher rate, in this section that corresponds to the ternary stage. So when the material begins to deform at a higher rate and the deformation begins or it becomes more excessive in nature, then generally what we do during creep test is we will stop the testing. We will not allow the material to fail, because the strain introduced during the creep test in the stage 1 cannot be avoided in an application. Meaning, when you put a material, when you begin to employ a material in an application, the load is instantaneously imposed on the material and the material begins to deform. So this is observed in the stage 1 of the creep. When you use a material in an application, when you employ a material in an application, the stage 1 or the deformation introduced by the stage 1 cannot be ignored, because once you introduce the material, it experiences a mechanical condition at a given temperature, and only after the stage 1 you get into the steady state case. So this stage cannot be avoided in an application. And similarly, the overall life of the material in an application is rather spent in stage 2. So this can also this stage can also cannot also be overlooked during the application. So the stage 1, it cannot be overlooked or it cannot be ignored, because once you introduce the material, the stage 1 is experienced by it. And secondly, the stage 2 is where the material spends most of its lifetime in an application. The one stage that can be ignored is the tertiary stage. So when you have a material in an application that has been employed for a very long time, and after a certain duration the material begins to deform excessively. When you notice the material begins to deform excessively and you see that this deformation is bothering other components in an application, then instead of allowing the material to fail, you stop that application, you then replace the material. So that is how it is usually done in the realm of the application, or in the area wherein the high temperature material is used. So instead of allowing the material to completely fail in an application, you regularly look for the deformation exhibited by the material. Since the tertiary stage is preceded by the steady state condition, for a larger duration of time during the lifetime of the material, there will not be a significant change in the deformation or the dimension of the material. So you have a high temperature material used in an application. For most of its duration or most of its lifetime, there will not be a significant change in the dimension of this high temperature material. Once the material begins to deform excessively, the rate of its deformation begins to occur excessively, it means that the material has now moved into the tertiary stage from the steady state stage. And once you realize that, instead of allowing the material to fail, you stop the application and then you replace the high temperature material. And for this reason, the creep test generally will not continue till the material fails. So once you experience an accelerated creep, or once the material begins to deform in an accelerated manner or begins to exhibit a high amount of creep or high amount of strain, the creep test is stopped, and then the focus is rendered to the strain exhibited by the material in the stage 1 and the life of the material in terms of the stage 2. So to put it simply, the creep test will not be carried on till the material fails. The creep test will be stopped once the material begins to deform excessively, meaning once the material gets into the third stage of the creep curve, the creep test is stopped. And now, based on the other sections of the curve that we have, particularly the stage 1, we understand the deformation that the material would exhibit within the application, the deformation that is unavoidable when you use the particular material in an application, that we understand. And secondly, from the duration the material spends in the steady state condition, we will be able to estimate the life of the material in a given application. So this is what we do in creep testing. We avoid the failure of the material. We stop the creep testing once the material enters into the tertiary stage. So these are the two characteristic features of creep testing. One is you avoid failure. Secondly, you stop the creep testing when third stage sets in. So these two features, when you talk about the creep testing from the standpoint of the testing of materials, this characterizes the creep testing. Now, there are similar tests that you could perform when you want to focus on the time that is required for the material to fail. So when you want to largely focus on, I want to understand the failure of the material at high temperature, then you can perform the similar test. However, creep test will not be super suitable for it, because when we described creep test, we talked about the one of the factors that should be maintained constant is the constant stress. So constant stress was one of the condition we began, or we ensured that it is imposed on the material during creep testing. So this means before the failure of the material, when the material begins to deform geometrically, when the material or when the geometry of the material begins to change, or when the necking sets in, the stress that is required to deform the material also correspondingly changes. And since we have used constant stress condition, then the tertiary stage is still prolonged. So that means when you want to test the failure of a material using conventional creep testing setup, then it will be sufficiently or unnecessarily prolonged, considering that we have assumed such a setup, meaning we have assumed a constant stress condition for the creep testing. And since this constant stress changes with all the geometrical change behavior that is exhibited by the material, and correspondingly with that geometrical changes like necking, the constant stress that we have applied changes, it means that the deformation till the material fails unnecessarily, it's prolonged when you use the creep testing setup to understand the failure of the material. So therefore, a new approach is adopted within the framework of the creep testing. A different approach is adopted in order to study the failure of the material at high temperature. So instead of focusing on the life and strain, when your focus is on, instead of focusing on these two aspects, instead of focusing on this, when your focus shift to the failure of the material, then you have to make some changes to the creep setup or the consideration that you have made for the creep testing in order to understand or efficiently understand the failure of the material at high temperature. So one such important consideration that you have to make when you want to study the failure of the material is associated again with the stress. So we saw that when you consider a constant stress condition, then any deformation that precedes the failure of the material, according to that deformation, say necking, if you have necking that sets in before the failure, the stress accordingly is reduced, and therefore the duration of the test is unnecessarily prolonged. Now this we want to avoid, and since our focus is not on the life of or the strain of the material, since our focus is on the failure of the material, within the creep testing setup, we want to make some changes in order to study the failure of the material efficiently, not by considering overall life of the material or overall behavior of the material, but just we want to focus on the failure of the material. So what changes should we have to make when our focus is not on the life of the material or high temperature life of the material or high temperature strain of the material, but just the high temperature failure of the material is what we will be seeing in this lecture. So the important change that we make is again associated with the stress, as it is the stress that prolongs the duration of this testing when you have a normal creep consideration. When you have a normal creep consideration, it is the constant stress that prolongs the overall test duration when you allow the material till it fails. So in case of this particular test wherein we want to focus on the failure of the material, the stress that is employed is varied. So in this test wherein the failure is of the primary importance, the stress that is used is significantly higher than the ones considered for the regular creep testing. So what you essentially do is, in the creep setup or in the creep framework, the one factor that you would change in order to study or focus the failure of the material at high temperature is you increase the stress that is involved to a significantly higher degree. So this test approach, which is carried out in a setup that is similar to that of the creep, wherein the temperature is involved, wherein you are going to measure the strain with respect to time. So all these framework would remain the same. The only change is you have shifted your focus from life and strain to that of the failure. So in such a case, the difference is you would be employing a stress condition or a mechanical condition that is significantly higher than the one that you would use for a normal creep consideration. Now this testing is referred to as the stress-rupture test. Stress-rupture test. So the only difference between a creep test and the stress-rupture test is the amount of stress that you use. So this amount of stress or the mechanical condition is the differentiating factor between the creep test and the stress-rupture test, and the rupture here refers to the failure. So in this test, what we are largely interested is in the failure of the material, and particularly the time taken for the failure of the material. Now when you compare the creep behavior or the behavior of material during creep testing to that of the behavior of material during stress-rupture test, it is largely noticeable to us even when you consider the simple representative curve that you would get from these two tests. So this is just a schematic representation. Both the creep test and the stress-rupture test is carried out in the similar framework, meaning you would have a constant temperature and a constant stress that is being involved, a constant mechanical condition that is being involved, and a constant temperature that is being involved, and the temperature in both cases are higher than the ambient temperature. However, the stress is of a significantly higher range in the stress-rupture test when you compare it to the creep test, and whatever change in the behavior that you observe in the material is primarily because of this stress. And if you could recollect, we have already seen what is the influence of stress on the creep rate, and so it will not be difficult for you to conceive what would happen when you increase the stress of the material for a given temperature. Now let us try to schematically plot the difference in the behavior of the material. So first one, let us consider an average stress condition that is usually used in the case of the creep behavior or the creep testing. So it will look something like this. you would have your instantaneous creep, transient creep, a large amount of steady state creep, and finally your tertiary creep. And like we discussed earlier, these tertiary creep, once the tertiary creep sets in, the creep testing, overall creep testing process is stopped and the analysis is continued. Now this is for the creep behavior of the materials, or the creep, this would be a conventional outcome of the creep testing. Now let us see how the similar curve would look for the stress rupture test. Now in case of stress rupture test, the stress is significantly increased, so that means it is a constant stress still, so you would have your instantaneous creep, which is followed by the transient creep. So let me replot it. You would have your instantaneous creep followed by your transient creep, but the minimal creep that should characterize your steady state condition is significantly increased. The minimal creep rate that should characterize your steady state condition significantly increases with respect to the stress. This is because we have already seen that with increase in stress, irrespective of the mechanism that is operational, or the creep mechanism that is operational, the stress rate, the steady state stress rate increases proportionately with respect to stress. So usually this increase is in the form of power law, and this power law wherein the n could be equal to 1 or 5 depending on the dominant creep mechanism. Irrespective of it, there is a proportional increase in the creep rate with increase in the stress, and that is the reason why you see a curve like this, and this point here is essential because this is where the material fails, or the failure of the material. So when you compare for a given material, so schematically when you present the creep curve and the stress rupture curve, of course you would observe the different stages. You would observe the tertiary stage, you would observe the stage 1 or the combination of instantaneous and the transient creep stage. The only stage that shows a significant difference is that the steady state creep stage, wherein the rate is significantly increased or noticeably increased when you increase the stress that is involved in the testing of, or involved in the stress rupture test. So this is the schematic difference that you would observe in the behavior of the material when you compare the stress rupture test to that of the creep test. Now let us see, or we can also quantify this by simple numbers. For instance, the minimal time that is required for, on an average, the minimal time that is required for a creep testing is close to 2000 hours. So this is the minimal time that is required for when you perform a creep test. The minimal time that you require to observe the onset of the tertiary stage is 2000 hours. This is again a minimal hour, and the average hour is 10,000 hours. So the average to maximum is 10,000 hours, and of course that could be depending on the conditions you have. That could be, say, 20,000 hours is also possible, but the range is between 2000 to 10,000 hours for a conventional creep testing. However, when you consider the stress rupture test, wherein your focus is on to understand the failure of the material and the stress is significantly increased, the maximum hour for the stress rupture test, or the maximum duration over which the stress rupture test is carried out, is 10,000 hours. So the stress is significantly increased in order to reduce the testing hours by half of the minimal creep test hours. So you have to increase, or in the stress rupture test, the stress that is involved, the mechanical condition that is involved is significantly increased in order to reduce the minimal hours that is taken for creep testing into half. So the maximum hours, or the maximum duration of the creep testing is below 1000 hours, which is less than, or which is half of the minimal hours that is required for the creep testing. Now this is in terms of the difference in terms of the duration of the testing. If you consider the strain experienced by the material during different testings, during creep testing, since we stop the material once the tertiary stages test set in, since we are largely interested in the strain introduced by the material during the stage 1 and also the life of the material during creep testing, and we stop the overall test when the tertiary stage test sets in, then when you compare the strain exhibited by the material during the overall creep duration, particularly when you stop the test once the tertiary stage sets in, during that time when your creep test is characterized in that way and you focus on the overall strain exhibited by the material during that creep testing, it will be on an average close to 0.5%. So during the overall creep testing, which could go for about 10,000 hours, the overall strain that is exhibited by the material will be just 0.5%. This is primarily because we cut off or we stop the creep test once the tertiary stage sets in, once you observe a significant change in the dimension or significant increased rate in the change in dimension, you stop the test, and for good reasons, because we want to consider the life of the material and the strain of the material. So in that case, typically during a creep test for a duration of thousands of hours, the maximum or the average strain that you observe is 0.5%. Again, this is because you stop the test once the material enters into the tertiary stage. We are not interested in the failure of the material during creep testing. So therefore, the maximum amount of strain on an average, the average strain that you observe during the creep test is 0.5% alone. However, when you compare or when you look into the stress rupture test, the strain is close to 50%. So here you are not stopping, in case of stress rupture test, you are not stopping the testing procedure once the material or the tertiary stage sets into the material. We are not doing that. We are allowing the material to fail, and after the material fail, you calculate, or when you calculate the strain exhibited by the material before it fails, it will be close to or more than 50%. So therefore, in addition to the behavior, in addition to the time taken for the overall testing, the strain observed by the material or strain exhibited by the material during the different testing also significantly varies. In case of creep test, it is just 0.5% strain. In case of stress rupture test, it is 50% or close or more than 50%. So the way we would calculate the strain in stress rupture test is after piecing the failed or ruptured material, we piece it up and then we calculate the overall strain exhibited by the material before it fails. Now, in this, the reason for performing this stress rupture test is to understand the failure or time taken for the overall failure of the material. So we want to calculate the failure time, the time taken for the failure of the material. So that is the primary focus of the the stress rupture test, and that is the reason why we see such a significant difference in the consideration that is made to the stress rupture test. So even though this test is performed in a framework that is similar to that of the creep testing, even though we maintain high temperature, we plot it in a similar way with strain and time, even though stress rupture test speaks largely of time dependent deformation, we increase the stress in order to understand the time taken for the failure. Now, when you have such a consideration, when your focus is just to calculate the time taken for the failure of the material at a given stress condition, or rather an increased stress condition at a particular time, then we have seen the duration of test significantly decreases. So when our focus is rather confined to the time taken for a failure, instead of studying the behavior of the material, instead of studying the life of the material, instead of studying the strain exhibited by the material, when our focus is largely confined to understanding the time taken for failure, then the approach that we take to understand or to calculate this value is largely dependent on the increased stress condition that we impose, and therefore the time taken for the stress rupture test is significantly reduced. And when you have a condition, or when you have a test wherein the time taken is significantly reduced, for a given duration of time, you can perform an increased number of tests. So when you have, say, a given duration of time, and when you want to perform a creep test and simultaneously stress rupture test, the number of tests that can be performed in case of the stress-rupture test will be significantly higher than the creep test. This is because the time taken for the creep or the stress-rupture test is much lower, or half of the minimal time that is required for creep test. Therefore, for a given duration of time, you can efficiently perform more number of tests. So the number of tests that can be performed for a given duration is increased when you consider just the time taken for the failure or stress-rupture test alone. And similarly, the cost of the equipments that are required to perform the stress-rupture test is also, when you compare it to the creep or compare it with the creep test, is rather minimal. Because unlike the creep test, wherein we focus on the smaller change in the strain, the smallest change in the strain over a prolonged duration of time, which requires highly sensitive equipments, since our focus in the stress-rupture test is rather largely on the time taken to the failure, then the equipment charges or the price of the equipment or the equipment employed in the stress-rupture test is rather minimal. So we have a minimal equipment cost in the stress-rupture test. And finally, the applications wherein the stress-rupture test plays a vital role is applications wherein the focus is largely on the failure of the materials rather than the deformation. If you have some application wherein the deformation is permissible, the deformation of the material during its lifetime at high temperature is permissible, but the failure is not, then for such a condition, or for such an application, we focus largely on the stress-rupture test. In case of creep, we focus on strain and the lifetime, and the application or the places wherein this material is used, when there is a huge amount of strain, the material then disturbs all the other materials, thereby causing the failure of the overall component. In such a case, people will focus, or we generally focus on the creep test. When the strain is also important component, when an excessive amount of strain leads to the failure of the overall component, then we focus on creep testing of the material. However, if we have an application setup wherein the strain is permissible, so the strain, any amount is permissible, and the only factor that concerns us is the failure. When you have such an application, then the preferable test that can be performed on the material is the stress-rupture test. So we've seen that the stress-rupture test is similar to that of the creep test. The only difference is you use a significantly high stress condition. So this means your steady state rate is accelerated and the material fails at, or the overall test finishes off at a very small duration of time. So the primary focus is to understand for the stress-rupture test is to gain an understanding on the time taken for the failure of the materials, and of course it has some relevant uses in the applications as well. Now when you plot in addition to this way of representing, since the stress-rupture test allows us to do a significant amount of tests for a given duration, considering that each stress-rupture test takes only half of the minimal time the creep testing takes, we are allowed to do numerous amount of tests, and these numerous amount of tests, the results of these numerous amounts of tests are rather presented in a unique manner. So this results from the several stress-rupture tests are presented as the combination of the stress and the time taken for failure. So the time taken for the failure is considered in the x-axis and the stress is considered along the y-axis. The constant stress that is considered for the stress-rupture test is considered along the y-axis, and the time taken for the failure is considered along the x-axis. And given the differences, since we are accumulating the different tests, we consider both log scale along the y and the x-axis. Now under such consideration, when you plot the stress, the constant stress along the y-axis and the failure time taken, or the time taken for the failure of the material along the x-axis, and you perform different or huge number of tests or stress rupture tests, the results generally would look like something in this manner, meaning at high temperature the time taken for the failure is quite low, and as the temperature decreases, the time taken for the failure also, meaning when the time stress decreases, the time taken for the failure, it increases. So this is a rather something that you can intuitively understand, and particularly we should remember that this is a log scale representation. So in a general sense, when you present your numerous data results or numerous results that you that you get from several stress rupture tests, you present it in a way wherein you include the stress along the y-axis and the time taken for the failure along the x-axis. Considering that you are collectively plotting numerous amounts of tests, you use log scale, and then generally there will be a linear dependence between the stress and the time taken for the failure. However, in some cases you would observe a condition like this: beyond certain stress amount or from certain stress levels, the time taken or the slope of the linearity between stress and the time taken for failure changes. So when you present the numerous data that you get from stress rupture test, in general case there will be a linear relation between stress and the time taken for failure, again when you plot it in the log plot. However, in certain cases there might be a significant difference, or there might be a noticeable change in a slope after a certain stress point, and this is because there is a microscopic change within the material. So whenever you get such a change in the slope of the curve that represents the relation between log of the stress and log of the time taken for the failure, this change in the slope, it denotes a microscopic or change in the microstructure rather. There is a microstructural change that brings about this change in the slope. If there is no microstructural change, the general trend that you observe from numerous stress rupture tests would be linear relation between the log of the stress and the log of the time taken for the failure. So each of these data points here, it represents each stress rupture test. And this is possible because we have sufficiently increased the stress that is required or that we involve in the creep testing, and that means the material fails quite quickly, and the time duration for the overall stress rupture test is small, or rather half of the minimal time taken for the creep test, and this allows for the numerous stress rupture tests, and this would give you a data point, something like sufficient data points to plot the relation between stress and the time taken for the failure. Now to wind this up, let us see one other reason for why we need to calculate the time taken for the failure, or what is the purpose does this stress rupture test serve. So we saw this stress rupture test can be of good use in an application where the focus is largely on the failure of the material but not on the deformation or the strain of the material. So that is one of the example for, or one of the reason why people would prefer the stress rupture test. The other reason is, as you can see, we can perform a large number of tests and we can relate the stress to the failure of the material. So that is the other reason why we can perform the stress rupture test. Now one other reason is, when you plot the creep rate, particularly the steady state creep rate, along the x-axis along with the time taken for the failure. So you plot the steady state creep rate along with the time taken for the failure. So TF be the time taken for the failure. Then you would observe the data points render a linear relation. Meaning, so supposing these are the several tests that you have performed, and you have calculated the creep rate exhibited during the stress rupture test, and you are largely focusing on the minimal creep rate during the stress rupture test, the minimal creep rate, and you are considering this minimal creep rate and relating it to the time taken for the failure. So this minimal creep rate and time taken for the failure, when you plot it along the y and x axis respectively, and you fit those data points, you would observe there is a linear relationship between the minimal creep rate and the time taken for the failure. So here I mentioned S for the steady state creep rate is because steady state creep rate is what gives you or renders you the minimal creep rate. So when you compare or plot the minimal creep rate with the time taken for a failure, you get a linear curve or a linear or a straight line. So this curve here represents that the minimal creep rate is then inversely proportional to the time taken for the failure. So based on or by exploiting the characteristic feature of the stress rupture test, meaning the stress rupture test takes a smaller duration of time when compared to the creep test, we perform several or numerous tests for a given duration of time, and we then plot the minimal creep rate exhibited by the material during the stress rupture test with respect to the time taken for the failure of the material. Then we would observe an inversely proportional relation between the minimal creep rate and the time taken for the failure. And now when we bring this here and use a proportionality constant, then the product of the minimal time or the minimal creep rate and the time taken for the failure is constant. So from the numerous tests or the stress rupture test that we carry or that we perform, we end up having a relation that states the product of the minimal creep rate and the time taken for the failure in a given test or during a given test is a constant. Now this relation then helps us to predict what would be the failure of the material when you have a definite creep rate. Supposing you perform one stress rupture test or a sequence of stress rupture tests, and then you are able to identify the constant for a given material. So you are able to identify from the product of the time taken for the failure and the minimal creep rate, which you would get from the numerous stress rupture tests that you could perform. You would then identify the proportionality constant C0. So these two values you will be able to calculate from the numerous stress rupture tests that you perform, and from that you can then identify or realize the proportionality constant. And once you have realized the proportionality constant for a material, then using this relation you will be able to predict for a given steady state creep rate what is the time taken for the failure. So now based on the stress rupture test allows us to calculate this constant value, and during the creep test you are able to calculate the steady state creep rate. And now since steady state creep rate and the constant of proportionality is known for a given material, now instead of allowing the creep test to go till the failure of the material or performing the creep test till the failure of the material, based on these two data you will be able to calculate the time taken for the failure. And this is possible because one, through the numerous creep tests that you perform, but essentially through this relation here. So this relation that states the product of the minimal creep rate during, be it creep test or be it stress rupture test, whatever test you consider, the product of the minimal creep rate and the time taken for the failure, TF, the time taken for the failure, is a constant. So this relation allows us to calculate the time taken for the failure even during creep test without performing the creep test till the material fails. So this relation here is referred to as the Monkman-Grant relation. So when you perform numerous stress rupture tests and get sufficient data points in order to relate the minimal creep rate with that of the time taken for the failure, then you will be able to identify the proportionality constant, which is a constant for the material. And now when you move on to the creep test and identify the steady state creep rate, then based on this relation you will be able to calculate the time taken for the failure without performing or extending the creep test till the material fails. And this is possible through the Monkman-Grant relation. So what we have seen in this lecture is, we have seen a variant of a creep test that is referred to as the stress-rupture test. The stress-rupture test largely focuses on the identifying the time taken for the failure of the material. So therefore, the stress involved in the stress-rupture test is significantly higher than the one that is involved in the creep test. Now, since you have or you use higher amount of stress, then certain things changes during the stress rupture test, meaning particularly the time taken for or the duration of the test is significantly reduced. And when the duration of the test is significantly reduced, then you are allowed to perform a huge number of tests. When you perform huge number of tests, you observe there is an inverse proportional relation between the minimal creep rate or minimal strain rate and the time taken for the failure. And when you relate these two, you will be able to identify the proportionality constant that relates the minimal strain rate and the time taken for the failure. And using that, you will be able to calculate the time taken for the failure within the creep testing setup without allowing the material to fail or without performing the testing for a extended duration of time. And this relationship is this relation that allows us to calculate the time taken for the failure of the material during the creep test from the proportionality constant and the minimal creep rate is referred to as the Monkman-Grant relation. So we will build on this in the upcoming lectures. Goodbye.